we're going to learn how to balance redox reactions. In the fall, you learned how to balance chemical reactions, and we talked about the idea that matter's not created and it's not destroyed. It's just rearranged. Bonds are broken and reformed during the process of a chemical reaction. So we're looking at those same ideas here today, but this is a little bit more of a complicated reaction to balance. And the big picture idea is we're looking at a transferring of electrons from a substance that was oxidized to a substance that was reduced. And we're interested in the movement of electrons, and of course we can get a current and use it to make a battery, which we'll discuss later. So in this example, I am going to talk you through the steps for balancing redox reactions, and you have these steps written out for you on a blue handout that we gave you earlier in the semester. That handout has both the solubility rules from our solubility unit, and it also has table 12.1, which are the steps for balancing redox reactions. So if you have that sheet, please go ahead and take it out. You also will want to have your periodic table with you. And if for some reason you don't have those steps, you can go ahead and print off or copy down these steps here. The first step that we are going to do in a redox reaction is assign oxidation numbers to all atoms. So we're going to go ahead and take a look at our first example, and we will start by assigning oxidation numbers to everything. In this example, we have an acidic solution, and we have molecular iodine plus sulfurous acid producing the iodide ion and the hydrogen sulfate ion, or bisulfate ion. So step number one, I'm using my periodic table, and I'm using my rules for assigning oxidation numbers in order to assign an oxidation number for every chemical species in solution. Remember that oxidation numbers are a tool to determine where the electrons are moving. So for molecular iodine, the oxidation state is 0 because it is neutral and it is an element, a diatomic element here. For sulfurous acid, the first thing that I'm going to look at is the oxygen. I know oxygen is almost always going to have an oxidation state of -2. The only exception to that is if it's a peroxide. Remember, peroxide is this polyatomic ion here, where you have 2 atoms of oxygen covalently bonded together with an overall charge of -2. So each oxygen atom has a charge of -1. This is not a peroxide, therefore oxygen is going to have an oxidation state of -2. We can break this sulfurous acid apart to try to determine what the oxidation states are for the other elements. So we know we have hydrogen, 2 atoms of hydrogen times the charge of hydrogen plus 1 atom of sulfur with its charge plus 3 atoms of oxygen's charge, and all of that has to add up to an overall charge here of 0 because it's a neutral molecule. We know oxygen has a -2 charge here, which means we can look at hydrogen next. Hydrogen has only 2 possible oxidation states. The majority of the time, hydrogen has a charge of +1. The only time it doesn't is when it's a hydride combined with a metal. This is not the case here, so this hydrogen will have a +1 oxidation state. That means we have a +2 plus a -6, giving us a -4 charge altogether. What plus -4 gets us to 0? +4. So we know that sulfur's oxidation state is +4. So I like to write the oxidation state above each atom that we're talking about. So we have +1 for hydrogen, +4 for sulfur, -2 for oxygen. If we look at the other side, this one's easy. It's a single atom ion, so its charge is equal to the charge of the ion. In the next example, we have hydrogen with a +1 oxidation state, not a hydride. Oxygen's not a peroxide, so it's -2. And if we take a look at this one, I have a +1 plus 4 times -2, which is going to give me a -7 charge. We need this charge to add up and equal -1. So what plus a -7 gets me -1? +6. All right, now that we've assigned oxidation numbers to all of our atoms, we're going to go ahead and take a look at our second step. Step 2 is to determine what has been oxidized and what has been reduced. So again, it's going to be helpful to remember our mnemonic. A loss of electrons results in an oxidation. The substance that loses electrons, we say, has been oxidized. A gain of electrons results in a reduction. The substance that is gaining electrons, we say, has been reduced. So let's go ahead and examine our oxidation states. Iodine goes from an oxidation state of 0 to an oxidation state of -1. If we picture our number line here with 0 in the middle, we have a positive 1, 2, 3, on this side, and -1, -2, -3. What we see is that iodine is going from an oxidation state of 0 to an oxidation state of -1. Moving in this direction, we're becoming more negative, which means that electron was gained. So there was a gain of 1 electron. A gain of electrons is called a reduction. So we would say that iodine was reduced. In keeping track of our other electrons here, we look at hydrogen. Hydrogen went from an oxidation state of +1 on the reactant side to an oxidation state of +1 on the product side. In other words, it didn't change. Sulfur, on the other hand, went from an oxidation state of +4 to an oxidation state of +6. So sulfur's oxidation state did change. In order to go from a +4 to a +6, we see that sulfur became more positive. The way that an atom becomes more positive is by giving up electrons. So in the example of sulfur, sulfur lost 2 electrons, and a loss of electrons is called an oxidation. So sulfur lost 2 electrons and was oxidized. So we did number 1, we did number 2. The third step is splitting into 2 half reactions. So we're going to actually write out our oxidation half reaction and our reduction half reaction separately. And we're going to write an equation for each reaction, including the electrons involved. First half reaction that I'll write out is that of iodine. So we have molecular iodine on the reactant side, and we have the iodide ion on the product side. The first thing that I want to do here is I will go ahead and write out my electrons. I see that iodine gained an electron, and so if it's gaining an electron, that means it needs to go on the reactant side. So I'm going to put 1 electron on the reactant side here. The next thing that I need to do is balance the number of atoms here. The only atom I have is that of iodine. On the left, I have 2 atoms of iodine, and on the right, I have 1. So in order to balance it, I put a 2 in front of the iodine here. Now that balances the number of atoms. The next thing I need to look at, though, is charge. On the right-hand side, I have a total of 2 times -1, which means I have a -2 charge on the product side. On the reactant side, I have a neutral charged molecule and a -1 charge for the electron. So these charges do not match. In order to get the same charge on both sides, I need to change the number of electrons here, and this should be 2 electrons. Now I've got a -2 charge on both sides of the equation. So atoms are balanced, charge is balanced. This particular reaction here, where iodine is gaining electrons, is the reduction half reaction. The second half reaction that we need to write out is our oxidation half reaction. In the oxidation half reaction, we see that sulfur, we've got H2SO3, sulfurous acid forms the hydrogen sulfate or bisulfate ion. In an oxidation half reaction, we know that electrons are lost. Sulfur lost 2 electrons to become oxidized. So the 2 electrons that are lost show up on the product side. So I have to write in my electrons here. After doing that, I need to check and make sure that atoms are balanced and charge is balanced. So first I'll check my atoms. On the left, I have 3 atoms of oxygen, and on the right, I have 4. Because my number of oxygen atoms don't match, I need to balance them. If we go back and look at our rules for balancing redox reactions, we get to know we're at step number 4. It says balance the atoms that were oxidized and reduced. Adjust electrons if necessary. If any other atoms besides the redox atoms need balancing, balance here. We need to balance the number of oxygens with water. So if we don't have the same number of oxygens on either side, we can add oxygen by adding water. Now, this is an okay thing to do because if we look at the top of our page here, it says that this is an acidic solution. A solution is composed of a solute and a solvent. The majority of the time, like 99.9% of the time in this class, our solvent is water. So we know that because this is an acidic solution and it's aqueous, that there's plenty of water to go around. So it's okay to add water in order to balance oxygen. Back to the equation here. 4 oxygens on the right, 3 on the left. I'm going to add 1 H2O molecule. Now I have 4 oxygen on the left. If I take a look at my other atoms, I have 1 sulfur on the left and 1 sulfur on the right. That looks good. I have 1 hydrogen on the right, but on the left I have 4 hydrogen. So I need to fix that. In order to balance hydrogen, if we go back and look at our rules, it is okay to balance hydrogen by adding the hydrogen ion. It makes sense here when we look at this because this solution is acidic. We know that an acidic solution means that there is an abundance of hydrogen ions in solution. So what we're going to do is on the right-hand side, we're going to add the number of hydrogen ions that we need to in order to equal out our hydrogen, which in this case is 3 hydrogen ions. So now when I'm looking at my equation, I have 4 hydrogen on the left and a total of 4 on the right. All of my atoms are balanced at this point. Now I need to check my charge. On the left-hand side, I have a neutral water, neutral sulfurous acid, so overall charge equals 0. On the right-hand side, I have a -1 charge, -2 for my electrons, and a +3 for hydrogen. So overall, I have a charge equal to 0. Charge and atoms are balanced at this point. Let's go back to our series of steps here. We're at step number 6. This is not in basic solution, so we're going to skip the rest of step 6, and we're going to look at number 7. Step 7 says to balance electrons. We have to make them the same in both half reactions because if a certain number of electrons are lost, that same number of electrons has to be gained. Electrons aren't created or destroyed in chemical reactions. We have 2 electrons that are gained in the first reaction and 2 electrons are lost in the second. So our number of electrons currently matches. We don't have to do anything there. In step number 8, we actually have to go through and combine our half reactions and cancel like terms. So we're going to go ahead and do that. Now, just a note here, guys, you will encounter this in some of your problems on your homework. Let's just say for a moment that instead of having 2 electrons here, this were 3. Let's just say for a minute this was 3 electrons. If this was 3 electrons here, and my number of electrons up here and down here didn't match, what I would have to do is multiply both half reactions by the least common multiple in order to get them to match. So in this case, with 3 and 2, they both go into 6. So I would have to multiply this entire thing by 2 and this entire reaction by 3. I'd end up with the correct number of electrons, and then I'd combine my half reactions. Now, in this example, I don't have to do that because we already had the same number of electrons. So I'm going to go ahead and erase that and get back to our current problem. Okay, so now we're on the step where we are going to go through and combine our two half reactions and then cancel like terms. So on the left-hand side, I'll combine all of my reactants. I have 3 electrons plus molecular iodine plus water plus sulfuric acid. On the right-hand side, I have 2 iodide ions plus the bisulfate ion plus 2 electrons. Oh, I'm sorry, I forgot to change this. This actually should be 2 electrons. I didn't change it back. This should be 2 electrons here. Plus 3 hydrogen ions. Okay. Now, I want to look through and see if any of the same things on the product side look like the exact same thing on the reactant side. So here, I have 2 electrons on the left, 2 electrons on the right. That looks good. If you ever get to this point and your number of electrons doesn't cancel, you know you did something terribly wrong. The number of electrons should always cancel out, and electrons should never be in your overall equation. I have iodine on the left. There's nothing to cancel it out on the right. I have water on the left, no water on the right. Sulfuric acid, no sulfuric acid on the right. Okay, so everything at this point has been combined as much as it could, and my overall chemical reaction will look like this. In order to determine that this is correct, we now need to do our last step, which is to rewrite and check atoms and charge, step number 9. So if we take a look at this, if I am checking my atoms, I've got 2 on the left for iodine, 2 on the right for iodine. I've got 2 hydrogen plus 2, which is 4. On the right, I have 1 plus 3, which is 4. I have 1 plus 3 oxygen, which is 4, and I have 4 oxygen on the right. For my sulfur, I have 1 on the left and 1 on the right. So our number of atoms is equal. In terms of our charge, we have an overall charge of 0 on the left, since all our molecules are neutral. And on the right, I have 2 times the -1, so that's -2. This is -1, and this is +3. So overall, on the right, we end up with a neutral charge as well. Okay. That is it, guys. Your answer to balancing this redox reaction in acidic solution is this right here, what we've boxed in. Nice job.